Hello, Math 201. This is the lecture for section 2.2, definitions of limits. And so we're going to explore just what the definition of a limit is, and we're going to do it mostly graphically. And so to kind of remind ourselves from that intro video of just kind of what motivates the idea of a limit, we're going to look at this kind of picture from the book. And so there's a couple things I want to point out. The idea is that average velocity can be computed by taking 2 points, that point 180 and this point 2, 128. And if you take the slope between those 2 points, so s of t1 minus s of t0 over t1 minus t0, that gives you the average velocity on a given between 2 points. And so that's how fast we travel from 1 second to 2 seconds, if these are our position functions at any point. And that's also the same thing as the slope of the secant line. And so the average velocity and the slope of the secant line are the same thing. And then as that point, that second point, so if we do it where there's a 1 second gap, the average velocity is 48. If you bring that point a little bit closer, and so at 1.5, the average velocity and slope of the secant line becomes 56. And you notice that as we get it closer and closer, this secant line more and more closely approaches a tangent line. And so right here it's 62.4. And so like I kind of said before, there's this kind of limiting process that's happening. And so once you reach the end, you get to the tangent line. And so the tangent line at the point 1, 80, so the instantaneous rate of change that this person is, or this object is traveling at 1 second, is given by the slope of this tangent line, which is the limit of the average velocity, or the limit of the secant slope of the secant line. And so that's the tangent slope, or the instantaneous velocity, and it's 64 feet per second. And so that's the slope of that line right there. And so we care about instantaneous velocity. We care about instantaneous rate of change. And so that's why we care about limits. And so the main point of this kind of background stuff is that we care about instantaneous rates of change. So we need limits. Limits are how we get these exact values. We take a limit, because you can't actually plug in 1 here, right? If you plug in 1, you'll get 0 over 0. And that doesn't make any sense. That's mathematically indeterminate. We don't know what that means. And so that's where the idea of limits come in. And so here's our working definition of a limit. The working definition of a limit is if you have a function which is defined everywhere close to a, so that's why it's working, because we don't really know what close means, right? That's kind of confusing, or not confusing, but ambiguous. This is an ambiguous term, but we're going to use just our intuition. It just means nearby. And f of x gets close to L. As x gets close to a, then we say the limit as x approaches of f of x, the limit as x approaches a of f of x is equal to L. And so in English, that's how we write it. The limit as x approaches a, so maybe this is a, the limit as x approaches a of f of x is equal to L. I guess I don't really need quotes there, but I put quotes on the a so that you know that's the letter A, not as in the article. And so what this is saying is that we want to know what the function is doing really, really close to that value a. And if it looks like the function value is getting close to some value L, then that will be what the limit is. But notice that it doesn't care what the actual value of the function is. In general, the limit as x, the limit as x approaches a of f of x does not need to equal what the function evaluated at a is. And so that's the key difference, is that the limit does not care what the value is. If these two things are the same, we say it's continuous, and we'll talk about that later. But in general, this is the case. So in general, they don't have to be the same. A lot of times they are, but in general, it doesn't have to be. And so let's find the limit graphically. That's going to be the main thing we're going to tackle in this section. And so the idea is we have some function. And so here's our function, but there's 2 holes. There's a hole right there, and there's a hole right there. It looks like from this graph that there's no value at 3, right? If you look at this graph, there's no function value. There's no black dot on there. But if you look at 2, it looks like the value should be there, but it's actually up here. And so f of 2, the function value at 2, is 5. But the limit as x approaches 2 of f of x. So what is the limit? Well, as we approach it from this side, it's getting really close to 3. And as we approach it from this side, it's getting really close to 3. So it seems like 3 is kind of the value that we're getting to. That's the y value we're getting close to. And so this is 3. And so we notice that these two things, the limit as x approaches 2 of f of x, is not equal to f of 2, because one is 3, this one was 3, and this one is 5, and those are not equal. How about another limit? Let's take the limit as x approaches 3 of f of x. What is the limit as x approaches 3? Well, it looks like it's getting really close to 4 from both sides. And so we'd say that this is 4, but the function value, f of 3, does not exist, is not defined. There is no y value when you plug in x equals 3. It's just a hole right there. And then for any of the other points, the limit really will just be the function value, right? So the limit as x approaches 1, the limit as x approaches 1 of f of x is just equal to f of 1, which is just 2. And so in this case, whenever it's kind of this continuous drawn line, then the function value and the limit will be the same thing. It's where we have these holes that things can kind of go wrong. And in general, this is a very important warning. So warning, maybe I'll even write that. Warning, warning, limits don't have to exist. And so here's a kind of, I guess we'd call a pathological example. So it seems simple enough, right? It's cosine of 1 over x. And what happens when you plug in x values that are closer and closer to 0 is that this number 1 over x blows up. It gets really, really big. And so what happens is as it gets really big, you're plugging in cosine of bigger and bigger numbers, but cosine always oscillates between -1 and 1. And so it's just going to get closer and closer, and it just becomes this kind of band. And so we would say that the limit as x approaches 0, the limit as x approaches 0 of cosine of 1 over x does not exist. And we normally do this as DNE. So the limit does not exist. That's what DNE stands for, does not exist. And so this is an example of a limit that doesn't exist. There are other ways for limits to not exist other than this kind of pathological weird behavior. And so let's take a look at that. And in order to do that, we need to define one-sided limits. And so a one-sided limit, here's the definition, and I'll let you read that later, but the idea is that the notation is, this means the limit as x approaches a from the right. So this is from the right. And so what that means is that we're plugging in numbers that are bigger than a. And so that's why we put a plus there. So it means plug in numbers that are bigger than a. And then this one is from the left, and we plug in numbers that are smaller than a and see what's happening. And so that's the definition. And so the idea is that, so when we do limit as x approaches a from the right of f of x equals L, this means plug in x bigger than a for the limit as x approaches a from the left of f of x. If that equals L, then that's plug in x smaller than a. And so there's a really important relationship between one-side limits and two-side limits, and that's given by this theorem. If f is defined for all a except for maybe at a, so it might have a hole, then the limit, the two-sided limit, right, where there's no plus or minus here, so that's a two-sided limit. So limit as x approaches a, if there's no plus or minus, this is a two-sided limit, or just limit, or just a limit. We a lot of times don't write two-sided. We only save the sidedness for one-sided. And so the idea is that a two-sided limit exists if and only if the one-sided limits are equal. So limit as x approaches a of f of x, that two-sided limit exists if and only if and only if, so that's what IFF means. So it's a definition, so they're equivalent. The two one-sided limits are the same. So a approaches from the left of f of x is equal to the limit as x approaches a from the right of f of x is equal to L. So this is true if and only if those things are true. So these things are equivalent. So that's how we can define whether or not a limit exists. And so here's an example. Let's do some one-sided limits. So the limit as x approaches 1 from the left of f of x. So what will that be? So if I approach from the left, that means numbers bigger than 1. So I'm approaching from over here. Then what happens to our y value? It gets really close to 2. And so this would be 2. And the limit as x approaches 1 from the right of f of x. So if I approach from numbers that are small or bigger than 1, so that's these y values, it seems like they're getting really close to -2. And so because these two things are not equal, they are not equal. So that means that the limit as x approaches 1 of f of x does not exist because the two one-sided limits are not the same thing. We could do another example. We could do the one-sided limit as x approaches 2 from the left. And you'll notice that if we approach 2 from the left or numbers smaller than it, we're getting to 0. If we approach it from the right, we're getting to 0, and it's the same thing. And so this is equal to the limit as x approaches 2 from the right, which is equal to the limit as x approaches 2 of f of x, which is equal to f of 2, which is equal to f of, which is equal to 0. So all three things are the same. The one side are all four things. The one-sided limits are the same as the two-sided limit is the same as the function value. They're all equal to 0 because it's this kind of continuous drawn line right there. There's no holes there. There's no jumping. Whereas here, there's kind of this gap. It jumped. The function jumped. And so that's why it's not going to have the same limit there. And so this is a classic example of what can happen. Then finally, let's do one last example. And so let's see what, let's do some one-sided limits. So what's the limit as x approaches 2 from the left? Oh, this is g of x, sorry, not f of x. G of x. What is the, and then let's do the limit as x approaches 2 from the right of g of x, and the limit as x approaches 2 of g of x. So the limit as x approaches 2 from the left, it's getting really, really close to 2 as we approach it from the left. And so this is going to be 2. If we approach it from the right, that's this part, right? These are the ones that are to the right. And so that corresponds to these y values up here. And so it's getting really close to 3. And so this limit, the two-sided limit, does not exist. By the way, we don't, so kind of aside, we don't do this. Don't do that. We don't say limit as x approaches 2 of g of x equals does not exist. We just say the limit does not exist. So don't put that in there. I'm going to erase it so you don't even think about it. But we just say the limit and then does not exist. What is the value? How about what is the function value? The function value at 2 is not there because there's a hole there, but it's filled in right there. And so right there, the function value g of 2 is actually 3. And then if we do the same thing for the limit as x approaches 3 from the left of g of x, we'll get that that is 3, and the limit as x approaches 3 from the right of g of x, that will be 2. And so the limit as we approach 3 does not exist. The limit as x approaches 3 of g of x does not exist. And then what is the function value at 3? What is actually g of 3? G of 3 would just be 2 because it's filled in right there. And so this is a classic example and should be able to get you through all the homework. All right, have a good one.